Okay, now I'm going to show you how to use base 10 blocks for multiplication. So starting off, once again, very basic. If we have, say, 3 times 5. Well, we teach our students that 3 times 5 means 3 groups of 5. 3 groups of 5. So, 3 groups of 5. So I'll do 1 group of 5. 2 groups of 5. And 3 groups of 5. So, you can count 5, 10, 15. 3 times 5 equals 15. Or, we definitely want to begin to move those into an array, which is made up of rows and columns, and always makes a rectangle. So when we put them like this, then this represents our 3 rows of 5. 3 times 5 is 15. And then we can talk about the commutative property of multiplication, which doesn't matter which order the factors are in, you will get the same answer. So 5 rows of 3 is also 15. So that's, where we're going to start with base 10 blocks and multiplication, but then we're going to be able to build up and go into our 2-digit multiplication. So I want to represent 14 times 12. And we're going to do this using our base 10 blocks. So the first thing we want to do is take our 2 factors and build them with our base 10 blocks. So 14 is represented by a 10 and 4 ones. There's my 14. 12 is represented by a 10 and 2 ones. Now remember a minute ago that we did the array and we made our rectangle. So this is going to be along the same lines. We're going to work within that same thing and build our array. So this is 14, also known as 10 plus 4 when we use our expanded form. This is 12, also known as 10 plus 2. So when we use our base 10 blocks to do this multiplication, we do it the same way we do on an area model, which I'll show you in just a moment. But so we'll start here with this 10 times this 10. Well, 10 times 10 is 100. So I'm going to slide in that 100 there. Then here we have 4 times 10. 4 times 10 is 40. So we'll slide in those 4 tens for 40. Then here we've got 10 times 2, which is 20. 10 times 2 is 20. Slide those in that way. And we're going to continue that, filling that in so that it makes our rectangle, because our area models form rectangles. So finally, here we have 4 ones times 2 ones, or 4 times 2, which is 8. So we'll fill that in to, and I'm using the different colors because it helps it stand out a little bit. 4, 6, 8. So this is the image that you get when you do 14 times 12 using your base 10 blocks. So I want to look at a couple of things here. Well, first of all, we don't have our answer yet because we have our factors, our original factors still up there. So I like to just pull those away. That was the original factor 14. This was the original factor 12. This is the product that's left. So we can simply add this up, count it up, and get our answer. This was 100. 10, 20, 30, 40, 50, 60. So 168. 168. So 14 times 12 is 168. So when we do that with an area model, just so you know, even though it's not a base 10 block, I'll show you that. We do the same thing. We say 10 plus 4, 10 plus 2. We draw our lines, and then we multiply it. 10 times 10 is 100. 4 times 10 is 40. 10 times 2 is 20. 4 times 2 is 8. And then we add those up. That's 168. So, and then as we build up to our standard algorithm, if we do this partial products, 2 times 4 is 8. 2 times 10, which is what this 1 really is, 2 times 10 is 20. Now we're done with our 2. Then we're here. This is 10 times 4 is 40. And 10 times 10 is 100. Do you notice that it's the same numbers here that it was there? And then you add that up, and you have your 168. Okay? And then finally, standard algorithm. 4 times 2 is 8. 2 times 1 is 2. 2 times 1, which is 10, is 20, but we're going to put that in the tens place here. So 2, 20. And then you're finished with your 2. So we're going to put a 0 here because this 1 is not really 1. This 1 is really 10. So we're putting our 0 there. Then we multiply. 10 times 4 is 40, but 1 times 4 is 4, and thus the 0 there. Erase that. And then finally, 1 times 1 is 1, but when you think about it as 10 times 10 is 100, that's why you're putting this 1 over here in this 1's place. And then when you add that up, 168. So that's using base 10 blocks, area model, partial products, and standard algorithm for multiplication.